Welcome, my name is Christian Pora, and this is a presentation about the distributed deep learning by Horovod service. The service belongs to work package 6 of the NEANIAS project, that is core services. As part of the artificial intelligence services, the main goal with Horovod was to expand the AI science gateway, that is C3.1, with a development environment suitable for distributed deep learning. The distribution of the training process is highly beneficial when working with large machine learning models, as the training of these models could take anywhere from days to even weeks. Horovod allows us to shorten this training time significantly. It was highly important that the integration of Horovod with the other artificial intelligence services is seamless and that the distributed deep learning fits nicely into the workflow that the AI Science Gateway supports. Before getting into the details behind the service, a few words about Horovod itself. It is an open source distributed deep learning framework. It was originally developed by Uber, who sought a way to train their large neural networks easily and efficiently. Horovod is quite flexible as it supports TensorFlow, Keras, PyTorch, and a variety of other frameworks. It can be run on-premise, in the cloud, or even on top of Apache Spark. The framework is also quite easy to use. It enables the training of our models on possibly hundreds of GPUs after just a few lines of code changes. According to the benchmarks posted on the official website, Horovod can achieve great scaling efficiency when working with even more than 500 GPUs and some of the most widespread neural networks and datasets. Horovod utilizes a so-called data parallel execution, meaning that our training data is divided into multiple subsets. These subsets are then used on our worker nodes to train the same replicated model. At the end of each batch computation, our model parameters are synchronized between the workers to keep our model consistent. Based on their research, Uber decided to utilize a technique called ring or reduce with Horovod. This algorithm allows the worker nodes to average gradients and disperse them to the other nodes without the need for a parameter server. During the training process, each of the workers will both receive and send data to their peers. The number of times this happens is in relation with the number of workers. This method is not only network optimal, but it is also easy to understand and adapt. Horovod utilizes the message passing interface and NVIDIA NCCL for the communication. Here we can see the architecture we use for the Horovod cluster. As you can see, the cluster consists of a number of interconnected virtual machines. Upon these virtual machines, the necessary software components are initialized within Docker containers, making this a highly portable solution. I have mentioned previously that Horovod utilizes data parallel execution, meaning that our training data must be distributed among the nodes of the cluster. In order to efficiently achieve this, we need some form of file sharing. We choose to apply the Network File System Protocol, or NFS, for this purpose. Among the nodes of the cluster, we appointed a master node, and this Horovod master virtual machine will host an NFS server, and this will distribute the training data over to the other nodes of the cluster. This appointed node will also host a Jupyter Lab development environment, which will provide an interface for controlling our cluster. In order to keep the presented architecture reliable and up to date, we have set up an automatic testing environment for it using GitLab's CI/CD capabilities. These automated pipelines validated the source code, deploy the architecture in a test environment, execute a set of tests on it, then terminate the resources. These pipelines are automatically executed currently on a weekly basis, which helps us ensure that any kind of software decay that happens doesn't disrupt our service, and that we can easily and effectively continue its development over time. Monitoring is highly important with any kind of computer system, but it is especially so in our case because we are dealing on one hand with deep learning, which is a highly resource demanding operation, and on the other hand, we do not have a single machine but a cluster of machines. So in order to track all of their resources, we needed some kind of monitoring system. For this purpose, we have integrated Prometheus and Grafana-based monitoring solution into the Horovod cluster, which allows us to quickly and easily track the resources of any of the nodes of the cluster. We can see information ranging from our CPU and memory usage to the highly important data about the GPU utilization and even network traffic. And all of these are highly important to keep track of when performing distributed deep learning. Horovod has been integrated into the NEANIAS AI gateway as a choosable server option. This portal is based on Jupyter Hub, and it intends to support users in the design and development of machine learning solutions. It offers a variety of different environments, the first one of which is a model development environment using TensorFlow and Keras. And after users have developed their possibly large models, they can efficiently train them by relying on the Horovod option and performing the training in a distributed manner on a remote Horovod cluster. But let's see how all this works in practice. The first step is to visit AI Gateway at the address ai-gateway.neanias.eu. Second, we have to sign in with Keycloak. You have multiple choices. You can either log in with EGI check-in or with Neanias. In the Neanias case, you can also use Microsoft and Google accounts. Upon logging in, you are greeted by the numerous different environments AI Gateway provides. I have mentioned previously that AI Gateway is based on Jupyter Hub. Jupyter Hub uses so-called spawners in order to start the single-user servers of its users. There are a variety of different spawners available: Docker spawner, Cube spawner, SSH spawner, and so on. Now, for our purpose, we needed to be able to provide multiple different environments, and different environments needed their own kind of spawner. In order to realize this, we decided to use a so-called profile spawner as the main component of AI Gateway. This allowed us to create these different environment choices and attach different spawners to these different choices. To put this into the perspective of the workflow that AI Gateway supports, users would typically would want to start their work with the very first environment, which is for model development using TensorFlow and Keras. Now, this environment is basically contained in a Docker image, which means that the most efficient way to supply it to our users is through Kubernetes. For this reason, we use the Cube spawner to start a JupyterLab instance within a pod on the Neanias Kubernetes cluster. Users can effectively work in this pod while they develop their machine learning models. And after they are done with this development, they will have to train their models. When working with large machine learning models, training them could take a significant time, days or even weeks when executed sequentially. But we can significantly reduce this time by distributing the training process, which is exactly why this workflow was expanded with Horovod. Distributed deep learning is a very resource demanding operation, which is exactly why we had to pay great attention when developing the previously presented architecture for the Horovod cluster. Granting users access to this Horovod cluster is not as easy as just spawning a pod in a Kubernetes cluster. We have to connect them to a remote cluster running in the cloud. For this purpose, we choose to apply a so-called SSH spawner. This spawner will establish an SSH connection to the given remote cluster and then spawn a Jupyter Lab instance for the user. It will also monitor this server along the work and shut it down when the user has finished. As a second step of the workflow, the user can start to distribute the training using Horovod. For this, they would have to choose the second server option and simply click Start. Then the SSH spawner will spawn their server on the remote cluster and connect them. After a short loading time, AI Gateway connects us to our Jupyter Lab instance on the Horovod master node. Within this environment, we have our usual options. We can either work in notebooks or straight from the terminal. On the left side, we can see the file browser and more precisely the contents of the Horovod directory. The contents of this directory are shared among the nodes of the cluster using the previously explained NFS protocol. This makes it fairly straightforward and convenient to use the cluster, since users can simply add their new files such as training data and code to this directory, and it will be automatically shared among the nodes of the cluster. They don't have to worry about this. Upon startup, this directory will contain two different files. The cluster.txt is a human-readable text file that contains a summary of the nodes of the cluster and their most important resources such as GPU, CPU, memory, and storage. The other file, hostlist, is here again for convenience sake. By default, for the Horovod run command, you would have to supply the IP addresses of each and every node of the cluster, along with the number of processes to be started on the given node. The number of processes to be started is correlated with the resources used. For example, one GPU would mean one process, and similarly, one virtual CPU would mean one process. Now, if we have a lot of nodes in the cluster, this can get pretty tedious. We would have to supply each and every one of their IP addresses. Instead, we have this automatically generated file host list, which contains the IP addresses and the process numbers for each of our nodes, and we can simply supply this in our Horovod run command. Talking about Horovod run, let's finally see how the distributed training actually works in practice. I have prepared a small and simple training script for this purpose. This is one of the example training scripts that comes as part of the Horovod repository. It is a part of the Horovod cluster we supply. It can be found within the examples directory among with many other examples that nicely demonstrate the changes you have to perform on your code in order to execute it distributedly. To start the training, we have to open a terminal window. Horovod can be started using the Horovod run command on the command line. I have mentioned that Horovod utilizes MPI for internode communication, and the Horovod run command is actually built on top of the MPI run command there. So they have their similarities, but the Horovod run commands abstracts many of the different options and makes it quite easy to perform training distributedly. After we have typed Horovod run, we have to set a couple different flags. First, the MP flag, which stands for the number of processes. For this, we have to give the total number of processes. So, for example, in a cluster of 4 nodes with 1 GPU each, this would be 4. In my case, this will be 2. Next, we have to supply information about hosts. I have mentioned that by default, you would have to give the hosts IP addresses one by one and also their individual process numbers. Now, as long as you have just 2 nodes, this is not really a problem, but as you start to scale up your cluster, it becomes tedious. So it is exactly for this purpose that we included the host list file, which can be supplied with the host file flag. Next, we have to supply a port for the communication between our nodes. In the Horovod cluster we have developed, this value will always be 1, 2, 3, 4, 5. Horovod nodes have these ports opened between them in the network settings, and they use this for communication. Next, we have to supply the executioner, which will be Python in this case. And lastly, we have to supply the actual training script that we wish to execute. At this point, we can execute the command. Horovod starts to initialize. This training script is based on TensorFlow, so you will see output that is related to that. There can be quite a lot of error and warning text. And then our training starts. We can see all the steps being written out to the screen. While the training is still ongoing, I can quickly check the GPU utilization of my master node by uh, starting another terminal window and checking out the output of the command NVIDIA SMI. And here we can see that our V100 GPU card is currently at 81% utilization. Going back, our training has now finished. It took 5,000 steps. Similarly to the MPI run command that it is based on, Horovod run will also display identifiers in front of each and every line that we see in the output. The second digit within this identifier is what actually identifies the node that the output is coming from. As this training was run on 2 different nodes, we see 2 different identifiers as we should. This means that both of the nodes actively participated in the training. Now that we have seen how the Horovod cluster works in practice, let's see how one can gain access to such a cluster. The Horovod cluster has been recently onboarded onto the EOSC marketplace as a service under the name Distributed Deep Learning by Horovod. In order to find the service, simply type Horovod into the search bar. Once on the page of the service, you will be greeted with the About section, which provides a short summary of what the service provides. You can also find links to our webpage, helpdesk, our email address, and to the user manual. The user manual is a lengthy guide that goes into detail about everything you need to know in order to access and utilize the Horovod cluster. It is here on the service page that you can actually gain access to the resource. Simply click Access the resource and go to the order website. This will redirect you to the NEANIAS SMS system through which you can place a new issue as an access request for a Horovod cluster. We have multiple access modes available for the service. The simplest one is a limited time demo, in which case we provide access to a demo Horovod cluster hosted on the Hungarian academic cloud, LKH Cloud. This cluster consists of 4 GPU-enabled nodes. Currently, we offer this for 6-day periods. For long-term access, users have 2 different choices. They can request us to deploy a Horovod cluster on EOSC resources. In this case, the exact period length for which they gain access and the number of nodes within the cluster is up to negotiation. And the other case is the self-hosted access mode, in which case the user themselves will deploy their cluster in their own environment. For this, we provide a lengthy and detailed user manual, and we also provide technical consultation if they run into any problems or have any questions. Of course, it can be said about any of the access modes that users can reach out to us through our help desk or write us on our email address. With that, I would like to conclude my presentation of the Distributed Deep Learning by Horovod service. I thank you very much for your attention, and I hope to hear from you among the access requests for the service.